Hello, everyone. So my talk actually will focus on the impact of sea ice on water level forecast and how to include it in a global operational water level forecasting system. First, I want to take this moment to acknowledge our co-author, Keith Thompson from Dalhousie University. It's very unfortunate that he passed away earlier this summer. And in the past, he helped us a lot in the development of the global operational water level forecasting system. So how to control the green button? Cool. I'll start with the introduction. Our primary goal is to use a global system to provide total water level forecast for all the Canadian coast. One particular challenge is that we have these two contradictory requirements. One is that the system needs to be computational efficient for ensemble forecast. This is very important. On the other hand, it also needs to be sufficiently complex to account for important physics. And in the past, we have developed effective and efficient methods to improve tides and include baroclinicity. But we still need to further address sea ice effects, particularly in the Canadian Arctic. So in this study, we seek to efficiently capture sea ice effect, evaluate the impact of ice effect on tides and the surge forecast scale, and investigate the contribution of dominant physical processes such as under ice friction, baroclinicity, and tidal surge induction. Oh, sorry. The main part of the series is to parameterize the surface stress in the presence of sea ice, and this is really done by a combination of the air ocean and ice ocean stress. And ice ocean stress is parameterized by the relative velocity between ice velocity and the surface ocean currents. To take into account this term, we are not going to run a coupled ice ocean system, which is not suitable for computational efficiency. The simplest option is to take it directly from external ice ocean system. But there is potential large inconsistencies for the tides because tides are very sensitive to different model setups. And to overcome this issue, we first decompose the relative velocity into a tidal and a surge component. Surge components are taken directly from the external model. For the tidal component, we derive a transfer function that describes the response with the tidal ice velocity to the surface tidal currents. And this function has a scale factor AT and a rotation angle phi. And we inferred them by scaling and rotating the ice and the tidal ellipse so that their semi-major axes are equal. And this approach is illustrated on the bottom right panel. And here the blue and the red shows the predicted ocean and ice ellipse from external ice ocean system, which is a quarter-degree global ice ocean prediction system, GEOPS at ECCC. So the black one is predicted by the transfer function, and we see here the black agrees well with the red one, and this indicates the transfer function is a good approximation. So in this slide, the lower panel illustrates the evolution with the derived 1 minus scale factor squared for the M2 tidal currents from GEOPS during 4 continuous winter months. And we see that this quantity actually reflects the mobility of predicted sea ice. As it approaches to unity, it represents the predicted landfast ice. And in the upper panel, we also show the observed frequency of landfast ice occurrence. And we see there are, in general, reasonable agreements. And lastly, I want to mention that we found that this transfer function or the response with the sea ice relative to tidal currents is not very sensitive to the accuracy of tides in the external ice ocean model. This is very important because apparently the quarter degree external model is not skillful in tides. For observations of total water level in the Arctic is very rare. And in efforts to make available observations as much as possible, we collected data including hourly tide gauge record, bottom pressure records, and monthly tidal constants from various institutes and publications. And in total, we used 61 stations, and we ordered them into 3 subregions. One is Arctic, second one is the northern North Atlantic and the Hudson Bay. The third one is the Northwest Atlantic. The bottom left panel shows the data availability since 1957. So we can use all these stations to validate the ice-induced variability in tide. And our model simulation period covered 3.5 years, and stations with available data are shown by the red, and we use these stations to validate the sea ice effects on storm surges. So next. First, let's look at sea ice effects on tides. And we first calculate the normalized amplitude anomaly and the phase anomaly referenced to their corresponding values in September. So the quantity in March represents the maximum modulations in the amplitude and the phase. Amplitude showing the top and phase shows the bottom. And we have 2 basic model runs, run AIO forced by the combination of air-ocean and ice-ocean stress, run AO forced by the air-ocean stress only. So by comparison, we can see that the adding sea ice generates much stronger seasonal modulations in the M2 amplitude and the phase. And for the amplitude, they are generally reduced near the coast, indicated by the cool color. But for the phases, the sea ice generally delays the arrival of the M2 tidal waves in the Arctic, indicated by the red color. But it's opposite in the Hudson Bay. So on top of this plots, we also show observations by the circles. And their comparison are further plotted as a function of station code. I remember that in the Arctic, we start from the northwest with Greenland and going around the Arctic clockwise. Then we start from the northern North Atlantic and goes into the Hudson Bay. Then it's the Northwest Atlantic. So observations are shown in black, run AO in blue, and run AIO in red. So by comparison, we see great improvements, and we see adding sea ice generally reproduced the observed modulations in M2 amplitude in the Arctic and the Hudson Bay, and also the phase delay in Arctic and the phase advance in the Hudson Bay. But we do notice that the model missed the amplitude modulations at station Shediac, which is located in a narrow strait in the Gulf of St. Lawrence. This could be due to the insufficient model resolution from both the external and the present models. I want to add that our model has 1/12 degree resolution. So to further explain the results, we look at the sea ice-induced displacements with the M2 amphidromic systems in March for 4 years. And they are shown by the arrows in the right 2 panels. And in general, we see that there are some interannual variabilities, but the main features are similar. The largest displacements occurs in the eastern Siberia Sea. where the epidromic points move close to the coast by up to 125 kilometers due to strong ice-induced tidal dispersion on the shallow shelf. The second largest one occurs in the center or Arctic, and these two displacements are responsible for the large-scale features with the modulations in the Arctic. And another area I want to talk about is the Hudson Bay, and we see that one with the epidromic points D, it moves to the coast where reflected waves travel. And this is consistent with the theory, consistent with frictional effects on Taylor's problem in a semi-enclosed basin. And this one is responsible for the phase advance in the bay. And in addition, there are also displacements with the degenerate or virtual epidromic points over land, which are difficult to show. Okay, so next we conducted process-oriented experiments to examine the effects of individual processes. Clearly, as expected, we see the largest contribution comes from under-ice friction, and tidal surge interaction due to bottom stress is negligible, and the other two are comparable, but they act quite differently. The tidal surge interaction due to the ice ocean stress occurs mainly in March, when we have maximum ice cover and also strong winter storms generated strong surface currents contribute greatly to the nonlinear interaction. Well, baroclinicity mainly occurs in September when the existence of pycnoclini stabilizes the water column, reducing the tidal dispersion into turbulent processes. Lastly, we look at the CIS effects on predicting storm surges. We know that for storm surges, a large fraction comes from the inverse parameter effect, which is not affected by the ice ocean stress. So to better realize the CIS effect, we have removed it from both observations and model predictions. And here we present the observed and predicted wind-driven water level and 5 stations where we see noticeable CIS effects when there are storms. And again, by comparison, we see great improvements, and especially it's up to 1 meter and station tag to attack. But we do see some limitations. The model overestimated the surges, like at Prudhoe Bay. And we found that this is due to underestimated ice velocities. So in summary, so we have developed an effective and efficient method to include CIS effects in global total water level prediction systems, and the method successfully reproduced observed seasonal modulations in tides in the Arctic and the Hudson Bay. And the physical reasons include large displacements with the epidromic systems due to the under-ice friction acting mainly in the shallow water. But there are also non-negligible contributions from baroclinicity and tidal surge interaction. And also, lastly, the method also reproduced well the ice-induced surge attenuation. But we do see some limitations could be related to insufficient breakup of sea ice during large storms. Okay, thank you.
So we'll do one very, very quick question.
What data set do you use for storm surge to evaluate this?
Data set?
What data set are you using when you say it's reducing by 1 meter storm surges in Tuktoyaktuk and Alert in the sea surface height? Like, what data set are you using to compare?
What data?
Yeah, like
it's from tidal gauge.
Sorry?
Coastal tidal gauge.
Okay.
Is that answer your question?
Mm-hmm.
Yeah.
Good.
Okay, thanks very much.